Okay, let's do some minerals. Allison, you are top of the list. You want to pick one of these and let me know what the composition is? Or pass?
Yeah, do you want like one of the end members?
Well, the mixed composition, for olivine and orthopyroxene. Spinel is an end member, magnetite's an end member, dioxide is an end member. Plagioclase would be a solid solution.
I'll do olivine because it's right there.
Okay.
So olivine, I have Mg or Fe2, and then SiO4.
Right. And olivine, the olivine mineral.
Yep.
Let's see. Kelly, do you have a favorite here?
I'll do spinel.
Okay.
Open it up. MgAl2O4. Is that right?
Okay, very good. Who's up next? Scott Govain.
I'll do diopside.
Okay.
That is MgCaSi2O6.
Yeah, I put the calcium before the magnesium because I'm going from the largest site to the smallest site. So that's the larger octahedral site. That's a smaller octahedral site. That's a tetrahedral site. But the composition you gave me was fine. Who are we up to? Mariah.
Yeah, I can do plagioclase.
Okay.
NaAl Si3O8.
That is a plagioclase end member.
Do you want me to give you the other one?
Would you please?
CaAl2 Si2O8.
Yeah. So sometimes you'll see this written NaCa. I don't know. Al Si 4O8. Sometimes you'll see it written like that, right? That really doesn't tell you a whole lot, right? Doesn't really tell you what is mixing in those phases. This is in my view, a better way to explain the composition of plagioclase because it makes it explicit that it's mixing molecules of albite and anorthite. With something like olivine, you don't have to worry about it because it's a single site and they're mixing. But with plagioclase, it's a coupled substitution, so it's a little more confusing there. Where do we get to? Scott Flanagan.
Magnetite is Fe3O4.
Okay. And Kira, I think you got orthopyroxene.
Okay.
Or unless you want to pass.
No, I can do it. It's FeMgCa, and then the second site you can have iron or magnesium, and then it's Si2O6.
Hang on a second, I gotta go turn the lights back on. Obviously, I'm not moving around enough. So for orthopyroxene, typically there's very low calcium in orthopyroxene. There is an orthopyroxene moderately high, very high temperature called pigeonite. So this forms at temperatures of like 1,000 to 1,200 degrees. So way up there, and especially in iron-rich compositions. So normally when I think of orthopyroxene, I think of just FeMg 2 Si2O6. But it is true, it has calcium in it, and especially at higher temperatures, that can be important. Okay, what I thought I would do today, bit of an experiment, I think this is going to work, is I wanted to look at the crystallization and chemical trends. I want to run some melts experiments with some crystallization trends of a fairly primitive, just typical basalt, foliatic basalt, And then I want to run the same experiment, except using a basalt that might be more typically formed in a subduction setting. And I'm going to take those data, I'm going to plot them on an AFM diagram. I mean, ideally, I would have you all run MELTS, but MELTS is very, very, very finicky. And I think it's easier if I just do a demonstration. You'll see how this is going along. And then after that, I was thinking you could get back to your problem set. This is all related to the problem set. And you could work individually, work together, take a break, whatever you prefer to do, okay? But let's do the, let me see if I can get MELTS running here. Oh, let's see, so I need to share my screen. Okay. And go to terminal. Let's see. Make this bigger. Well, I don't know if that's going to matter. Let's see. Okay, so it's going to run MELTS Rhyolite, and it says, do I want to run this? And it's going to open up an interface in a minute. Okay, so you can all see that. So our composition is going to be over here on the left. So I'm going to open, and I think I called this thing primitive basalt 1, PB1. Okay, so let's just take a look real quickly at what this looks like. So SiO2 49.2, so low silica. MgO 10%, okay, that's high magnesium. A bunch of other stuff in here, intermediate aluminum content, 16%. It's got some sodium. It doesn't have very much potassium in it. It's got a fairly low water content. Hang on a second, I'll move this out of my way. Let's see, so we want to check to make sure that I haven't screwed up something here. So we're gonna start, what we're gonna do is we're gonna take this liquid and I'm gonna have stuff fractionally crystallize from it. So I'm gonna lower the temperature from 1400 to 700 degrees in increments of 10 degrees. And I'm gonna do this at 1 kilobar, and that's not gonna change, it's just at a constant pressure. And as I fractionally crystallize stuff out, the liquid is going to evolve. And so what we want to look at is how does the liquid evolve, and then why does it evolve that way? Okay, so if I hit compute here, it just sets the increments for pressure, done. And now an important point here is for intensive variables for the FO2 constraint, I am not doing anything here. I don't have an FO2 constraint. And so this is going to be fairly low FO2, and that will become important. So let's run this. And it runs until it runs into an error because it gets down to really low temperatures and everything blows up. That's kind of the nature of thermodynamic calculations. But what I have done here is I've saved all of the data. Let's see, so this is PB1. And so this is I ran this, like half an hour ago. These are the data that you get out of it. So here is the temperature, and here is the liquid composition. Clearly nothing is crystallized here until we get down to temperatures of about 1240 degrees, because these are all constant. But we want to plot this on an AFM diagram. Okay, so we got to do exactly the same thing with the weight percent FeO, Fe2O3, and the NaO and K2O that we do in the problem set. So I am going to insert a column. I'm going to make this equal to my FeO content plus 0.9 times my Fe2O3. Take that, copy it down here. Okay, and now I'm going to come over here, insert a column. And this is going to be sodium plus potassium. Paste all that stuff in. And now what I'm going to do is take these data, I'm gonna run over to turn plot and paste special values. Okay, and then I've got to get, where's FE total? Here's FE total. Turn plot. Edit, paste special values. Okay, and now I need to get magnesium. Where's magnesium? Right there. And this one I can just paste in directly. Okay, there we go. So here's our AFM diagram. Here I'm going to take a little screenshot of this. Grab that. Oh, looks like I already did this. Maybe I already did this. Can go back here. We're going to put this into PV1. Okay. So that's our trend. And we start out with low alkali content, so we have to be starting off over here. And we have to end up over here where there's high alkali content, not very much iron and magnesium. Okay, so what do you notice about this trend? Oh, who are we up to? Christina, you there?
Yes.
Okay. Oh, great. So what do you notice about the trend? Anything that you want to call out?
It really increases in F, and then once it reaches that peak, it drops down.
Yeah, so it's got this interesting phenomenon where it's got a little hump there. It increases in this direction, and then it turns around and comes down again. And why do you suppose it increases in this direction? We up to Amanda. What do you think might be precipitating to cause the composition to move off in this direction?
Elements with magnesium in them.
Minerals, sure. And
Yeah, or minerals, yeah.
what kind of mineral would you anticipate might be the first thing to precipitate out of this?
Probably olivine.
Yeah, that's what you'd think. Like most basalts, you think, well, okay, olivine is going to be the first thing to precipitate out. Olivine composition is going to be down here, doesn't have any alkali. It's got a high magnesium content. And so if olivine is over here, and that's the only thing that's precipitating out, then the composition has to move away from it. Now, as the composition moves away, the composition becomes more iron rich. The olivine becomes more iron rich. So the olivine composition is steadily moving up in this direction too. And that's why this thing tends to have this weird curvature to it. There's other stuff that's going on too. There could be other things. And then it turns around here. That means, what does that, let's see, Jessica's not here. Allison, do you know, can you speculate why it turns around here?
So that's iron right at the top.
Yep.
I don't know. I was kind of thinking just about like the density of various minerals.
Mhm.
So once the denser minerals kind of bring out all that iron, then it would kind of start driving the composition to be more alkaline.
Right. So I think what you're saying is that as stuff gets more and more iron rich, as the minerals become more and more iron rich, the curvature is going to start to curve over. Has
Yeah.
to do that.
Exactly.
This one seems like a pretty, and that's true. That's absolutely true. This is a pretty abrupt change, though. It suggests that something else is coming in. Kelly, do you want to speculate on what that something else might be?
An iron-rich mineral, but which mineral that is, I have no clue.
Exactly. No, you've got it. Absolutely got the concept down perfectly. If it moves off in this direction, you got to be removing a magnesium-rich mineral. But if it shifts here, it suggests you're pulling in something else that has a composition that's up here somewhere. And now you've got two minerals that are co-precipitating, and the composition gets driven away from that combination of minerals. So at first it's going off in this direction because you have magnesium-rich minerals. You bring in this iron-rich mineral, and then the thing curves over. And does anybody, I'll just throw this open to the class, does anybody want to speculate on what that mineral might be?
Could it be
Potassium.
Can't be potassium. If it's potassium, it'll move away from the alkali site. So we're looking for an iron-rich mineral. And somebody else was saying
Magnetite.
something.
Sorry, I think I unmuted myself at the same time. Could it be magnetite?
Yes, I heard 2 votes for magnetite,
Could it
3
be-
votes for magnetite. Anybody else want to?
I'm just saying that because we saw so much in our lab yesterday.
And exactly right, because your subduction lab, you look and you see those oxides and there's magnetite in there,
Like
right?
in almost every slide I saw some.
Yes, absolutely. And so what'll happen is eventually magnetite will come in, and really the question is, when does it come in? When does it come in? In this primitive basalt, what did I say about it? Low FO2, okay, so it tends not to stabilize ferric iron. It takes a little while before magnetite stabilizes. And then when magnetite forms, then it drives off in this direction. It doesn't have to be magnetite. Also, actually, I'm not positive in this case. It might be ilmenite. I don't know if you remember in the Harker diagram problem set that we saw ilmenite start to precipitate. Of course, ilmenite has a lot of iron in it also, and that'll drive it off in this direction. Whether you get ilmenite versus magnetite depends a lot on FO2, because ilmenite, let's see, I guess ilmenite is FeTiO3, and that iron is Fe2+. Right, whereas magnetite, Fe3O4, has 2 ferric irons to it and 1 ferrous iron. Okay? Let's see, I wonder if we can figure this out. So where does iron, I'm gonna look at titanium. So iron really starts to drop right around here. And titanium is starting to drop. So this is probably actually ilmenite. It's probably ilmenite in this case. But I'm not positive. We could look it up, except that I don't want to take the time right this second. Or it could be both ilmenite and magnetite, but it's got to be an oxide. That's generally what drives this composition away from this region. Combination of magnesium-rich minerals and iron-rich oxides. Okay, now back to our rhyolite melts, and I'm going to quit out of this because it's so buggy it will probably crash again. And I'm going to run this again. No. And now I'm going to open primitive basalt 2. Okay, and now for this, what do we have here? So I increase the aluminum content. So I'm trying to model the kind of basalt that might form in a subduction zone. Subduction zone basalts, for reasons we don't need to go into right now, have higher aluminum contents in general than tholeiitic basalts, more like basalts. Same kind of magnesium content, and I added some water to the system. So now I have 5 weight % water. It's actually oversaturated with water, but just to make sure that this is a really juicy melt that has been created by water fluxing of the mantle. And let's see, what am I going to do here? Don't need to do that. T and P, I need to make sure this is right. 1400 to 700, 10 degrees C. That just does that. Okay. Options, I'm fractionating the solids. FO2 constraint. And here I've got quartz phaolite magnetite +2. Okay, so quartz phaolite magnetite, that's a buffer, an oxygen buffer. There's a reaction among quartz, magnetite, and phaolite. that involves oxygen. And most of the mantle is thought to have an FO2, well, it's thought to buffer FO2 very close to that equilibrium. But it's really important that there are places where the FO2 can be higher or the FO2 can be lower. And one of the places where it's higher is in subduction zones, in the melting that occurs in subduction zones. And so what we're going to have is, instead of having FO2 as 0 with respect to QFM, it's going to be up at 2. So what's that going to do? That's going to make more ferric iron, and that's going to tend to stabilize oxides. So let's see if I can get this to run. Well, I know I can get it to run. Let's see when it fails. Okay. All right. Okay. So there we go. And I put this into this. Put the data into this spreadsheet. So now this is primitive basalt 2, and we got to do the same thing, right? Because that's the nature of science, right? You gotta never quite get what you want when you want it. Okay, so we just did that. We're going to do the alkali. Okay. That. And clearly something didn't work here because it lost some compositions. Okay, so now what do I need? I need to grab the alkali here. And we're going to go back to turn plot. And we're going to paste that into the alkali site. Oops, paste special. Values. And we need FEO. Got to paste special on that. And you already saw what the change was right there. And magnesium's going to shift this around a little bit. So changes it like that. Okay, so, and there's probably some, wackiness. I probably didn't copy all the, yeah, I don't know. So let's see, where do we leave off? Allison, Kelly, Scott, Govain. No, you've volunteered magnetite. Mariah, Mariah. What do you notice about this trend that's different from the previous one?
That little tail that was shifting the amount of iron isn't as prominent.
Exactly. Yeah. And so what does that mean, Scott Flanagan?
It's not precipitating something with as much iron.
Well, if it were not precipitating something with iron, it would probably be a very magnesium-rich mineral.
Yeah.
If it precipitates out a magnesium-rich mineral, it'll move away from it.
Well, I just meant it's not precipitating as much as our last example.
In a proportional sense, that's true.
Yeah.
What do you think has to be precipitating, though, early on to drive it in this direction?
The aluminum. Is that what the A is, aluminum, right?
No, the A is alkali, and so it
Okay.
can't be precipitating something with alkali, or it drives it off in the other direction. If it's moving towards a corner like this, it means that you have to be precipitating something basically in the tangent. Take the tangent, and it's got to be something that's off in this direction. Hang on, I got to move and remind the room I'm still alive. Okay. Let's see, Kira.
So is it starting on the right side then, you said?
Yeah. Oh,
Oh,
sorry.
yeah.
Yeah. Starts.
I thought it was the other way, sorry.
Oh, yeah.
So then this way it's getting more iron and magnesium rich.
Starts out iron and magnesium rich, and it's moving off in this direction.
Yes. So getting less and less.
Right. Kira, you want to jump in with some thoughts on what might be happening here?
So it initially gets more iron, so perhaps it was precipitating forsterite first and then just a little bit of phalite
Uh-huh.
to drive it away from that as well.
So that'll move it just that little tick mark up here, little bit here.
Right.
And
And
then,
then if you're doing both forsterite and phalite at the same time, then it'll drive it down to the alkali feldspar site.
that would be true. It turns out that you can't precipitate two end members of a solid solution. You can only precipitate the solid solution. And the solid solution, olivine, in equilibrium with this liquid is always more magnesium rich. The liquid is always more iron rich than the olivine or the orthopyroxene, or clinopyroxene for that matter, that precipitate out of it. So any precipitation of olivine, orthopyroxene, or clinopyroxene, even though they're solid solutions, even though they contain iron, is going to tend to drive it away from the magnesium. Well, some point down here. A mixed composition, but much more magnesium than the liquid is. Let's see, we have two here. Christina.
Am I
Offer some
still-
ideas?
I don't know. I was thinking the exact same thing, so I don't really know what else more to add to that.
Okay, let's go back to, hang on, let me just cut this out. This over here. We're gonna go here. Grab this, put it there, make it a little bigger. And I'm gonna copy this. I'm gonna put it right over here. Oops, what just happened there? Okay, so those are our two trends. I'll move this one over here. All right, so here is our first trend. They start off in essentially on almost the same point. I guess this one has a little less magnesium. Maybe I screwed something up there, but this one goes off in this direction and then turns around. And what was the reason that we said we thought that it was actually making this curve here?
Was it-
Amanda, do you remember what we were talking about at that point?
Weren't we saying that magnetite was precipitating or crystallizing?
Or ilmenite, but some kind of
Okay.
iron oxide.
Yeah.
And so if magnetite or ilmenite and any magnesium silicate, olivine, orthopyroxene, clinopyroxene, if they're precipitating together, then the combination, if that average composition of what is precipitating is over here somewhere, the composition will be driven away from it. So here we see there may be a little bit of evolution, but basically the composition gets driven away from that sideline very early on. So Allison, do you want to speculate on what that means in terms of the precipitation of oxides, timing of precipitation of oxides?
Well, in the first one that we looked at, it looks like the oxides kind of started precipitating like a little bit after the first magnesium mineral. And then in the second one, it looks like the magnesium didn't really precipitate for that long before the oxide started precipitating as well.
Exactly. That is exactly it. And that's the only point that I wanted to make here. That when you look at relatively low FO2 melts, so things that form in mid-ocean ridges, ocean islands, those kinds of melts, the oxide doesn't get stabilized for quite a while. Now, I know it seems like, well, that's a very small distance up here compared to the number of points that you see over here. This is actually a fairly small temperature range. Remember, we went down to 700 degrees and the fractionation of this liquid is just going crazy. A lot of the fractionation occurs in this first little leg here. And so the oxides come in relatively late. They come in relatively late because it takes some ferric iron to, usually it takes some ferric iron to stabilize them. Whereas in subduction zones, what you find is that you can precipitate a little bit of, now I can't remember what precipitates first, whether it's olivine or pyroxene. You precipitate a little bit of that, but almost immediately the liquid gets saturated in an oxide. And as soon as that happens, the oxide is enriched in iron and the composition goes off in that direction. Now, does anybody remember what the name of this trend is and the name of this trend is? Who do we have? Kelly, do you happen to, I don't know if you looked at the videos that I posted. I know somebody did because there's a couple views, but.
I don't know.
Okay. Scott Govain, do you know what those trends are called?
Sorry, I was having Zoom troubles. I have not seen the videos yet, no.
Oh, okay. And Mariah, do you want to offer? Otherwise, I'll just tell you.
No, I haven't watched them yet.
Yeah, okay. So this term, this trend here is called the tholeiitic trend. So this is tholeite up here. And a tholeite is just a mid-ocean ridge basalt. That's how I think of it. That's not true. A tholeite probably has some technical definition such that mid-ocean ridge basalts tend to be tholeiites. But that's how I think about it. It's sort of a typical mid-ocean ridge basalt kind of composition. And the tholeiitic trend occurs at relatively low oxygen fugacity. This term is called the calc-alkaline trend. And so this is characteristic of ocean islands and mid-ocean ridge basalts. The mid-ocean ridges, they show this iron enrichment trend, early iron enrichment trend. Sometimes it goes way up here and then comes down. Whereas the calc-alkaline trend, this is for subduction zones. This is what you see across subduction zones. And it shows this, the perfect calc-alkaline trend starts out with the most primitive compositions here and basically goes straight towards the alkali corner. So that's a very important distinction in the chemical evolution of volcanic rocks that we see. So for example, you might go to, I don't know, some ancient origin and you find a bunch of igneous rocks and volcanic rocks ranging from mafic to felsic, and you say, oh, well, how did these volcanic rocks form? One of the ways that you can do it completely independently of what you think the tectonic setting is, or what the distribution of the rocks is, you can measure their chemistry and you can see, do they follow this kind of expected tholeiitic trend or do they follow this calc-alkaline trend? And if they follow a tholeiitic trend, well, then you start thinking about, well, this could be ocean crust, or maybe there's some kind of hotspot source for it. If it shows a calc-alkaline trend like this, well, immediately you would start thinking about subduction zones. And that is one of the things that people do when they go to these ancient origins where the rocks are not always as texturally distinctive, or they're all sliced up, or you have little fragments and you're trying to reconstruct exactly what was going on. One of the things you can do is to look at these different trends. And like I said, the different trends are a reflection of when oxides start to precipitate out of these systems. And when the oxides start to precipitate out depends a lot on the oxygen fugacity. Higher in subduction zones, lower in mid-ocean ridges and ocean islands. Okay. Any questions on this before I turn you loose on your problem set again? Well, hearing none, I will turn you loose on your problem set then.
I'm gonna do a fresh start on mine because you know how bad mine was last time. I'm on my PC though now, so I should have better luck.
Okay, that's good to hear.
Hey Matt, for this problem set, what exactly do you want, like, how do you want it turned in? Do you want it all in like one Excel document?
That would be fine.
Okay.
Whatever is convenient to you. In this case, I think an Excel document is like simple. And let's see, I was going to go and try to track down the actual that's my the oh yeah, the output here. Oh, I found it here. Sorry. This is so fun for me. I don't know if it's fun for you, but anyway, let's see. Share my screen. Okay, so this is the output of our run for the calc-alkaline system. So here's temperature, 1220 degrees. And at this point, it's just liquid and water. So this is supersaturated. So it's actually coexisting water and a silicic melt. And as we come down here, 1210 degrees, we now have added olivine. And the olivine has a lot of magnesium, 0.91 and 0.09 iron. So that's 1210 degrees. When we come down to 1200 degrees, now we have olivine and water and this mineral spinel. But if we look at the composition of the spinel, we find that it has a lot of this Fe with the three little apostrophes, meaning ferric iron. And so what this is a ferric iron spinel, and the most common ferric iron spinel is magnetite. Magnetite is a member of the spinel group family, and it has ferric iron. We were just looking at that this morning. And so this is telling you that at 1220 degrees, the very first crystal to form is olivine, and almost immediately 10 degrees lower or 20 degrees lower, whatever it is, spinel magnetite starts to form with a high iron content that drives everything towards the alkali side. I'll see if I can track down the table for the output for the tholite, and then we can see exactly what's precipitating, whether it's ilmenite or magnetite or both. I think I have to rerun this though. Okay, I found it. If anyone's interested in looking at the pholeitic crystallization sequence, I'm going to pull that up just real quickly. So let's see, 1250. All I have is, oh, yeah, here we go. 1240. I just precipitate out olivine and keep going down temperature, olivine, 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 olivine. So you can see there's like a lot of olivine that's precipitating out of this liquid before anything else does. Oh, and the composition is 87.5% forsterite. So it's very nearly pure forsterite. Olivine, olivine, olivine. Dang, it's a lot of olivine. Oh, clinopyroxene and feldspar, because so these are joined. Olivine, clinopyroxene, feldspar, olivine, clinopyroxene, feldspar, olivine, clinopyroxene, spinel. There we go. So the first oxide to form is this magnetite. It's a ferric iron rich spinel. It must have some titanium in it. Yeah, it's got some titanium in it also. That's why titanium starts to go down. So that's the difference, right? Had all of that period of olivine and then olivine, clinopyroxene, feldspar precipitation before the oxides joined the assemblage at a much lower temperature. Okay. Yeah, so for the first plot, the composite plot with Galapagos and Iceland, you do not have to distinguish the data.
Okay, good.
Yeah, no, I know what a pain that would be. Just consider it all one big data set.
Okay.
And it's just because Iceland doesn't have particularly primitive rocks in it. They're fairly evolved. And so I added Galapagos so you could see a lot of primitive rocks in there too.
Okay.
And so then for Tonga, I said composite, but that's just a holdover from copying and pasting the Galapagos plus Iceland. It's not really a composite plot, it's just a plot. And then the same thing for the Southern Andes. And so you'll have 3 ternary plots. I don't care if the symbols are same colors or different colors, as long as they're distinguished according to which one is Iceland Galapagos, which one's Tonga, which one's Southern Andes. And then I think you'll have 6 Harper diagrams, right? So so you'll have FeO versus MgO, and then you'll have the alkalis versus MgO. So those 2 diagrams for each of those 3 systems.
What are the units? Do you know for the Harper diagram?
It's all weight percent.
It is all just weight percent. Okay.
Yeah. And we don't have to do any correction except for that. You got to multiply Fe2O3 by 0.9, but otherwise there's no monkeying around with converting to moles or anything like that.
All right, cool.
Okay, folks, I'm going to sign off now. Any last questions?
I'm all good. Thank you though, Matt.
Yep. Can I gauge, get a sense of how you feel a deadline of midnight tomorrow is going to work out?
I have to get through all the thought questions still, so I don't know how long that will take, but I could probably have it done by midnight tomorrow.
Okay, how about other people? Kelly, yeah.
That goes for me as well. I just have the thought questions left, and I think I could manage that by tomorrow.
Okay. Okay, well, so let's leave it at midnight tomorrow, and everybody take a look at the thought questions. And if you want an extension, then I will, just ask me for it, because I understand everybody's schedule is kind of crazy. And if I get a lot of requests for extensions, then I might just officially extend the deadline until the end of the weekend or something like that. But let's try to get it done by the end of Friday. And then also please do try to watch those videos if you haven't done that already. Okay, I will be in office hours tomorrow if anybody wants to continue working on this or really talk about anything else. Okay, bye.
All right, thanks, Matt.
Yep.
Thanks, Matt.
Bye, thank you.